Good morning, everybody. In the last class, we were discussing about the analysis, these small signal AC analysis of amplifier circuits. So we took up the common emitter amplifier circuit with an emitter resistance, and you know that the emitter resistance is being used to improve the stability of the bias, the transistor bias. And now let us continue the analysis of the same circuit. So please look at this figure. So this is the circuit which we have been analyzing, and the circuit is being analyzed without this capacitance known as the emitter bypass capacitance. That means the emitter resistance is not bypassed. So this is the equivalent circuit which we obtained in the last class, and from this equivalent circuit we got the input impedance at this point between this terminal and this terminal as beta times Re, this resistance, plus 1 plus beta into Re, so this one. And the input resistance is a parallel combination of, naturally, this R1 and R2 parallel combination and this Ri dash, which is given by this expression. So therefore the input impedance is this. Now let us look at the voltage gain. Let us find an expression for the voltage gain in the circuit. As you know, the voltage gain expression can be obtained by dividing an expression for V0 by an expression by Vi, and this can be analyzed using this equivalent circuit. So please note that, so this voltage across RC, that is V0, is minus beta IB into RC. Since beta IB is the current flowing inside, the current flowing through RC is minus beta IB into RC is the voltage, and the input voltage can be expressed, Vi can be expressed as IB into Ri dash. We know the expression for Ri dash, or if we know II into Ri. So please note that II into the whole of Ri is the whole input impedance, is equivalent to this IB into Ri dash itself, because there is no series resistance here. So hence we shall substitute this expression and this expression in the voltage gain expression and get the result. Therefore you get this as minus RC into beta IB, and that one divided by Vi. Vi is Ri dash into IB. Therefore, so this is equal to minus beta RC by Ri dash. And if you substitute for Ri dash, here you will get it as minus beta RC divided by an expression for Ri dash is beta Re plus 1 plus beta into R capital E. Now this is a fairly accurate expression for the voltage gain, and please note that the voltage gain is negative for the same reasons I gave in the last class. There is a phase difference of 180 degrees between the output and input. Now you can obtain an approximate expression for the voltage gain, and by these approximations, if Re is much smaller than R capital E, and since beta is much larger than 1, so you can neglect this, because of the first approximation you can neglect this compared to this, and beta and 1 plus beta are almost equal. Therefore, the voltage gain is going to be minus RC by RE. So this is because the same current almost flows through this. IB is negligibly small compared to this IC and IE. So the output voltage, the AC current, output current responsible for this output voltage is IC here, and the input voltage here is this voltage plus voltage across RE. If this is negligible, so the input voltage gets dropped across RE totally. Since the output voltage and the current passing through is almost same, therefore the output voltage is proportional to RC and input voltage is proportional to RE with the same proportionality constant almost, and therefore the voltage gain is RC by RE with a negative sign because the current flowing direction is opposite here. So because of that simple reason, the approximate expression for the voltage gain is minus RC by RE. And in case this is 5 kilo ohms and 1 kilo ohm, the voltage gain is equal to 1. And if this is 1 kilo ohm and this is 1 kilo ohm, the voltage gain earlier, if it is 5 and 1, voltage gain is 5, and if this is 1 kilo ohm and 1 kilo ohm, the voltage gain is 1 with a negative sign. So what is your comment about the input impedance? The voltage gain? The voltage gain is very low. So voltage gain is of the order of unity in the circuit. What is responsible for that? The emitter resistance is responsible for that. It's because the emitter resistance, the voltage drop across the emitter resistance is acting as a feedback. That means the voltage drop across this is acting as a feedback to the input side. And this voltage drop here is effectively decreasing the input voltage Vi that is applied across the base to emitter junction. You see this signal which is applied across base to emitter. So this is equal to this voltage minus this voltage. Therefore, this drop is effectively reducing this voltage, and a small fraction of it is being applied to the base emitter junction here. So because of this reason, the voltage gain is affected, voltage gain is low. And please note that for the same reason, the bias stability is improved. If due to some reason, if the collector current increases, the voltage drop across RE increases. I am talking about DC current, and the voltage drop across this increases, and that one reduces the voltage drop between base to emitter junction, and as a result of which the collector current is reduced. So this was a positive point. This is a positive point as far as bias stability is concerned. It is a positive point even for AC analysis if you want the amplification to be stable. Please note that the amplification is totally dependent on RC and RE. It's minus RC by RE. It is not dependent on beta. So the voltage gain is minus RC by RE. Its dependence on beta is very small. Therefore, if you change a transistor with beta equal to 100 and replace it by another transistor with beta equal to 200, it's not going to change the voltage gain. So voltage gain is going to be stable with this kind of arrangement, with this kind of feedback. But you are losing in terms of the gain. Gain is reduced now considerably. If RE is 0, the gain is RC by R small e minus RC by R small e. R small e is of the order of few tens of ohms, and RC is usually of the order of kilo ohms. Therefore, it gives you a very good gain. But because of this term RE, R capital E, the voltage gain is now reduced. Is it clear? There are two things discussed here. I brought in the stability of bias and the stability of gain, that is in making the gain of the amplifier independent of the transistor parameters like beta. And the third point is the reduction in gain because of the feedback. I will come back to this topic later. And now let us determine the voltage gain. Or this can be to a better approximation. So this term can be written as, we can add an RE here, and this is a better approximation. Only considering beta is much larger than 1, assuming that beta is much larger than 1, which is true. So the approximation expression is RC by R small e plus capital RE, which is in turn can be approximated to minus RC by RE because of this approximation. Now let us find out an expression for the current gain. So current gain expression can be obtained from the output current to, so input current ratio, from the expressions for output current to input current ratio. Now looking at the equivalent circuit here, the output current is beta IB and the input current is II, and II to IB, since this is the output current is, let me express it, output current is beta IB by the input current. Now if we know the ratio between IB to II, we can get an expression for the current gain. And please note that if here we are considering the current that is going into the terminal as the output current. If you follow the convention of the load current as the output current, there would be a sign change. Okay. So with the current going inside into the terminal as the positive current, that is I naught here, and that is equal to plus beta IB. It is in the same direction. Now here II to IB ratio can be determined because that is needed there in the expression. And when this resistance is Ri dash, please note that II gets divided between the parallel combination of R1 and R2 here and this Ri dash equivalent appearing between these two terminals. Therefore, IB is II into the parallel combination of R1 and R2 divided by the parallel combination of R1 and R2 plus Ri dash, because it is the division between these two equivalent parallel resistances. Now substitute this expression here. If you substitute that expression here, so you will get beta into R1 in parallel with R2 divided by R1 in parallel with R2 plus Ri dash as the expression for the current gain. Now, in the textbook you are following, that is Naschel's scheme. So this is expressed as an RB. So in which case it is beta RB by RB plus Ri dash is the expression, and Ri dash expression is given. Now I like to give you the relationship between AV and AI. Let me discuss about AV and AI relationship here. Please note that the voltage gain relationship can be obtained by dividing the output voltage by input voltage, and the current gain is can be obtained by dividing the output current by input current. And the output voltage and currents are related by RC. Okay, minus I naught into RC is V naught, and the input voltage and input impedance, input voltage and input current are related by Ri dash, Ri. So input voltage Vi is Ii into Ri. So because of these two relationships, you can have a relationship, a simple relationship between the voltage gain and current gain. So let me give this relationship. Relationship between voltage and current gains. The output voltage V naught is minus I naught RC, and the input voltage Vi is equal to Ii into Ri. Please note the current direction is current is the ingoing current. Therefore, the ratio V naught by Vi, that is AV, the voltage gain, is equal to minus RC by Ri into I naught by Ii, so that is the current gain. Always the voltage gain is equal to minus RC by Ri into the current gain of an amplifier. So once you compute one of these, the other one can be computed from the same relationship. Now let us obtain an expression for the output impedance. Output impedance is the impedance looking into these terminals without excluding RC. Excluding RC, the output impedance is the impedance looking into these two terminals between this point and this point, and with RC included, the output impedance is the impedance looking between these two terminals, with the input replaced by a short circuit. Now, if you replace the input over here, these two terminals over here, please note that there is no driving voltage on this side, and when you incorporate some driving voltage here, apply some driving voltage here, the IB will be current, and this current also would be 0. Therefore, nothing flows inside, no current flows inside. So because of this reason, the current that flows inside is 0. That means it is an open circuit and the impedance is infinity, excluding RC. If you include RC and apply a voltage source here and drive current, so the current that flows inside is the current of RC, that is the voltage applied divided by RC, that current, and this current is 0 because there is no driving input here. As a result, IB is 0, and when IB is 0, naturally this is also 0 and there is no voltage drop across this, and so this is like an open circuit. So any voltage applied here, no current flows through it. Hence RC is the output impedance. So excluding RC, output impedance is is equal to infinity. And if you include RC, output impedance is equal to RC itself. Now, so this is the analysis of the circuit, the common emitter amplifier circuit with self bias as the biasing circuit. Now please note that we have used an approximate model here, wherein beta Re is the input resistance and beta IB is the current dependent current source. Now in case you include R naught, the output impedance of the common emitter circuit, so this resistance comes into picture. R naught also comes into picture here. When R naught comes into picture, the output impedance changes and the expression for the current gain, voltage gain, etc. also change. I will give this problem as an assignment to you to solve this problem with R naught included. That means obtain an accurate expression or obtain accurate expressions for the voltage gain, current gain, input impedance and output impedance of a common emitter amplifier with self bias circuit.
Sir, if we select emitter resistance small enough such that the maximum collector current rating is not overshooted, then can the voltage gain and current gain be maximized?
There is a question there. When if Re is very small, is maintained at a very low level, we can at the same time get voltage gain as well as gain stability. So naturally, with reduced Re with a small resistance R capital E here, the voltage gain can be seen to be maintained at a reasonable level, and at the same time you can have some stability for the voltage gain. The voltage gain can be made to be independent of the transistor, that is the transistor beta. Yes, it is possible. That is how actually feedback is provided through a small emitter resistance Re. Some feedback is provided, and through that the voltage stability of the voltage gain and current gain, etc. are maintained in practice. Yes, it is a usual practice of feedback amplification. Any other question?
So what effect does it have when we include the bypass capacitor?
I am coming to that. Now, to reduce this problem of reduced gain through Re, we can include a bypass capacitance here, an emitter bypass capacitance. So what is the advantage? If you introduce a capacitance here, as far as alternating signals are concerned, and if the capacitance is large, let me use the symbol CE here, if the capacitance is large enough to make its impedance to be negligibly small, if it makes the impedance negligibly small, you can treat that it is a short circuit as far as alternating signals are concerned. But when you think of the bias and bias stability, so please note that you are interested in only the DC currents there, the operating point. Operating point means is the DC voltages and DC currents. So as far as the DC components are concerned, this capacitor acts like an open circuit in steady state. So at the beginning of the power on, there would be some transient, and the capacitor gets charged to a voltage, to a DC voltage that is equivalent to the drop across RE into IE, that drop, and its voltage is maintained at constant level. So even when an alternating signal is applied, for the alternating signal, its voltage doesn't change much if C is very large. So that is the reason why it acts like a short circuit as far as alternating signal is concerned. So with alternative current driving through this, the voltage doesn't vary. That RE into IE, the DC IE, is maintained at a fixed level. Therefore, you can see that the effect of RE is reduced, the feedback effect of RE is reduced or almost completely eliminated by using a large emitter bypass capacitance. At the same time, the bias stability is maintained because biasing quantities are DC quantities. Hence, we use a large emitter resistance to bypass the emitter resistance. The objective is to increase the gain of the amplifier while maintaining the stability of the DC biasing, or to maintain the stability of the biasing. And please note that as far as alternating signals are concerned, so the feedback is negligibly small, or there is no feedback. Therefore, the gain stability which I was talking about cannot be obtained by introducing a bypass capacitance here. So introducing the emitter bypass capacitance, we can increase the gain. So when the capacitance is introduced, for AC analysis, you can replace RE by a short circuit because it is a very low impedance, and if it is of the order of a few ohms or a fraction of an ohm, and this can be treated as a short circuit for all practical purposes. Therefore, in the equivalent circuit, when the emitter bypass capacitance is used, this RE is out. So this you can replace RE by a short circuit. And when you replace it by short circuit, the analysis boils down to the same analysis which we have done in the previous class. Or alternatively, you can use the same expressions for analyzing the circuit also. Please note that now RE will be replaced by 0. When you replace RE by 0, so you will get the input impedance as R1 in parallel with R2 in parallel with beta RE itself, and this part is 0. And now what's happening to RI? RI is now considerably reduced. Please note that this is of the order of 1 kilo ohm, and if RE is 1K, and if this is 100, this is 100 kilo ohms, 100 plus 1, it's going to be 101. And if R1 and R2 are large enough, so this input impedance is very large when this term is there. Now with RE bypassed, input impedance is going down to beta RE in parallel with this itself. So input impedance is considerably reduced with emitter bypass capacitance, and the expression is this, as I have explained. Now in the expression for voltage gain here, so this 1 plus beta RE is 0, therefore the voltage gain is minus RC by R small e minus RC by R small e. It's not capital RE. Please note that this is of the order of a few ohms, and this is a few, usually a few hundreds of ohms or a few kilo ohms. Therefore, this is going to give you a very high gain. And the current gain is the output current divided by input current, and now the ratio is the current division ratio is between R1 in parallel with R2 and this input impedance, and that is now beta RE itself, which is much smaller than this. Therefore, this current to this current ratio is almost unity, because this is a very small resistance. In the absence of this is a very small resistance, and the current division is such that almost this entire current flows into the base. Hence, this ratio is almost unity. Hence, the output current to input current ratio is almost equal to beta. So now the accurate expression for this can be straight away obtained from this expression. It is beta into R1 parallel with R2 divided by R1 parallel with R2 plus Ri dash now is going to be beta Re itself, which is very small. Therefore, current gain is also considerably increased. So, as far as the output impedance is concerned, there is no change, and with RC excluded it is infinity, and with RC included it is RC. If you are going for accurate analysis, including that parallel resistance across between the collector and the emitter terminals, so this is going to be R0. This would be R0, and this would be R0 in parallel with RC. We got an expression for expressions for these, including R0 in the previous class. Please note that when I discussed about the fixed bias circuit, the small signal analysis of the fixed bias circuit, amplifier with fixed bias circuit, the circuit is the equivalent circuit is similar. Therefore, the same analysis holds good here also, where RB is R1 in parallel with R2. Any questions? Now let us discuss about the emitter follower. There is an interesting circuit, so known as an emitter follower configuration for a transistor amplifier. The circuit is given like this. You can use either a fixed bias with an emitter resistance or a cell bias circuit, and there can be two resistances here, a voltage divider or a single resistance, it does not matter, and the input is as usual applied to the base, between the base and the ground, and the output is taken from the emitter terminal. So this is the place for the output. And these two are coupling capacitances. Input is applied here and output is taken here. So you will find that this circuit exhibits some interesting characteristics. You will find that Ri is very high, voltage gain is almost unity, current gain is very high, and interestingly, output impedance is very low, very small. And because of this reason, that Ri is very small and R0 is very small, Ri is very high and R0 is very small, this circuit is typically used for matching between a load and an amplifier. For instance, in an audio amplifier, in a public addressing system, you drive loudspeakers with the amplifier signal. And for the loudspeakers, usually the impedance is very low. The resistance is something like 16 ohms, 32 ohms, 8 ohms, and it is of that order. When the impedance of the loudspeakers is very low, that means the load resistance is very small, and if you apply that kind of load in a circuit, in a common emitter circuit like this, if you apply 16 ohms load here, and with RC is equal to say 5 kilo ohms, in the equivalent circuit, where is this load coming into picture? Load is coming in parallel with RC. How much gain do you get? RC in parallel with RL is very small, and the gain is going to be even less than 1. So it doesn't work. If you use this kind of a circuit there, it doesn't work. So in such cases, what we do is we include an emitter follower here, see that its output impedance is low, and then connect a low impedance load to it. So an emitter follower circuit is used for this kind of applications, matching purposes. Now let us find the equivalent circuit of this and analyze it. So this is RB coming between the ground and the base terminal, and here it is beta RE, this is capital RE, R capital E, so this is the equivalent circuit. Please note that if you have two resistances here, R1 and R2, in the equivalent circuit, you would have got R1 in parallel with R2. So RB is equivalent to R1 in parallel with R2. Now, with RE here, so this circuit is similar to the, I'm sorry, this is not the output impedance, output voltage. Output voltage is this across RE. So this is the output voltage. So that is the difference. Otherwise, the equivalent circuit is similar to that of the circuit with the emitter resistance. And we know that the Ri dash here is equivalent to, so this resistance in series with this resistance, and this resistance is 1 plus beta times Re, as we have already obtained. Therefore, this is beta Re plus 1 plus beta times R capital E. And the input impedance between these two terminals, that is Ri, now the input impedance of the transistor amplifier is now Rb in parallel with Ri dash, which is nothing but this expression. This is the input impedance. Now, how much is the voltage gain in the circuit? When this is Vi, the base current is Vi by IB is Vi by Ri dash. So that is this impedance, because this voltage is Vi. There is no series resistance here, therefore the voltage across this is also equal to Vi, and Ri dash is the impedance, therefore this is the current. And what about the output voltage? Output voltage is this IB and this beta IB, 1 plus beta IB into Re. 1 plus beta IB into Re. Now from this we can get the voltage gain as V0 by Vi as equal to 1 plus beta into Re into IB divided by Vi, and now if you substitute this equation, this expression here, in this expression you will get this as 1 plus beta Re divided by Ri dash as the voltage gain, and substitute for Ri dash here. This is the expression for this. Please note that this is equivalent to this. So the denominator is more than the numerator. As a result, so this is going to be less than 1. And when this is usually much smaller than this, therefore this is approximately 1. Voltage gain is approximately 1. It is because this input voltage is getting divided between, so this voltage between beta Re and Re into this 1 plus beta, and that is the output voltage. Therefore output voltage is a fraction of the input voltage, but that is a large fraction of the input voltage. Therefore voltage gain is almost unity, but actually it is slightly less than unity. We shall continue this discussion in the next class.